In this video, we're going to talk about a couple of important algebraic properties of a group. The first one I want to talk about just has to do with how we write the group operation. It's not so much a property as a convention, but it's a convention that's backed up by a property. How we write the group operation. So the old school way of writing down a product of two elements of a group is to write down, okay, let's say that A and B both belong to G, and we say A star B, that's what we call the product of A and B. Even if the operation isn't exactly multiplication, we often call the result of this the product. That's just convention. Okay, so that's a customary way of writing it. But there's a quicker way of writing it that we usually do. If we know that there's only the operation star, and we don't have any chance of getting confused by doing this, we'll usually write this as just A, B. Just jam the symbols together and assume that what goes between them is the star operation. So we will typically do that. We'll usually write A, B instead of A star B. So for example, if I want to write A star A inverse is 1, where 1's the identity element, I'll write that in shorthand as A inverse equals 1. Okay, another thing about how we write the group operation is what happens if we have three group elements, A, B, and C, all belonging to G. If I write something like this, A star B star C, technically that's ambiguous, because if I write something like that down, well, star isn't something that we can use to compose three objects, it's something we use to compose two objects. So I could talk about A star B, that's an element of G, and then compose that with C, or I could talk about B star C, which is also an element of G, and compose that with A. But if I write this, then it's not exactly sure what's meant by that. However, I actually will write expressions like this quite a bit of the time, and it's perfectly okay. Nothing falls apart, because if I mean A star B star C, or if I mean A star B star C, well, these are actually the same thing. They represent the same element. They're equal by associativity. So it's actually quite common to write an expression like this instead of parentheses AB times C or A times parentheses BC. And we can get away with this because both of these are known to be the same thing by associativity. So a lot of the time I will simply write this. Okay, so those are a couple of things about just how we write the group operation. Now, here's an interesting property of inverses. Each element of a group has exactly one. Exactly one. So you'll remember the properties of a group, the defining properties say that each element of a group has to have an inverse. What we didn't talk about was whether there could be maybe more than one inverse. But I claim that the properties of a group tell us that each element of a group has to have just one. And here's why. So here's a proof. Suppose A is an element of a group, and assume that B and C in G are two inverses of A. We know that A has to have at least one inverse, that's part of being a group. But suppose A has two of them. Okay, so then what do we know? Then we know that AB is equal to 1 and is also equal to BA. We also know that AC is equal to 1, which is also equal to CA. Both of those things are true because that's just what it means for B and C to be inverses of A. Alright, so we know that those things are true. But then that means that AB and AC, those are both equal to each other. So I can now write that down, that AB equals AC. Those two products are the same element of my group. And because they're the same element of my group, if I were to multiply this element by B on the left, I should get the same thing each side. In other words, if I were to take B and multiply by AB, I should get the same thing if I take B and multiply by AC, because again, AB and AC represent the same element of the group, because those are both the identity. But now I can use the associative property to regroup all of this. So the left side is really BA times B, and the right side is really BA times C. This is by associativity. So now, well, wait a minute, I have a BA here and a BA here, and one thing we established is that BA is equal to the identity. So each of those is equal to the group identity. 1B equals 1C. And because, so this was because B is an inverse of A. All right, but now because 1 is an identity, that means that B equals C, because 1B is B, 1C is C. So 1 is the identity, and that means that B equals C. But wait a minute. I assumed that B and C were just any two inverses of A. I assumed that up here. And I ended up showing that B equals C, which means if I have two inverses of A, they're really the same inverse. So really, this means that A has only one inverse in G. All right, so that's a nice fact about groups, that I always have just one inverse for each element. The third property I want to talk about, and this will be the last for this video, is cancellation. So I'm going to zoom out, put this over here, and we'll just talk about cancellation over on the right side. Okay, so here's fact number 3. Cancellation properties. So here's a theorem. If A, B, and C belong to a group, and AB is equal to AC, then it follows that B equals C. Now this looks an awful lot like what I had over here with AB equaling AC, and then I ended up with B equals C. But there you'll remember I was assuming that B and C were both inverses of A. So this is a little bit more general, but it's going to follow the same argument structure. I'm just going to do something a little bit different to prove this. This, by the way, is called left cancellation. Poor planning on my part there. Left cancellation, because it's telling me I can cancel the same element if it appears on the left side of a product. There's also something called right cancellation, and that is also a true theorem. I'll state that in just a minute. But here's the proof of this one. So assume that A, B, and C belong to G, and assume that AB equals AC. All right. Well, how could I reveal that B equals C? The idea is I want to try and get rid of the A somehow. Well, I do have a way of getting rid of the A by multiplying something. I can multiply by A's inverse, which now we'll just call A inverse. So because these are the same group element, AB and AC, multiplying on the left side by A inverse should give me the same result. So I know that A inverse times AB is the same as A inverse times AC. And now, by associativity, I can regroup and say A inverse A times B equals A inverse A times C. That, again, is by associativity. And now, because A inverse is the inverse of A, the part in parentheses just works out to be the identity. So 1B equals 1C, or the identity times C. So that's the property of inverses. And then because 1 represents the identity of the group, the left side is just B, the right side is just C. So this is the identity property of the group. And so I have exactly what I want. I know that B is equal to C. So now I know that if AB equals AC, then it follows that just B equals just C. I can drop the A from the left side. Notice that I am dropping the A from the left side in both cases, though. I'm not saying that I can drop A from either side, and it doesn't matter which side the A is on. If A is on the left in both cases, I'm good. And similarly, if A is on the right side in both cases, I'm good. As this theorem will state, if A, B, and C belong to G, and BA equals CA, then it's still true that B equals C. I'll leave off the proof of that one because it works pretty much the same way as this one. We just multiply by A inverse on the right rather than on the left. All right, so those are a few basic properties that we're going to use really often, so we want to get used to seeing them.